Thanks for the introduction. I'm Zhang from George Washington University. I will present our work, hardware assistant isolation in a multi-tenant function-based data plane. This is a collaboration with AT&T Lab Research, my mentors Abhigyan, Kaustubh, and my advisor team. NFA allows to run network functions as software on commodity servers in a cloud multi-tenant environment. Each tenant prefers to have their own network functions. For example, in VMware NXX NFA product, each tenant have their own virtual switch, virtual router, and firewall. Compared to hardware mailboxes, software-based network functions are easy to provide and deploy the required network functions for each tenant. One way is that we can run a network function inside a virtual machine or container. It can leverage the hypervisor or operating system to allocate the resources and do memory isolation across multiple tenants. But it has context switch or a cross-call overhead. Another way is that run a network function just as a function call. Comparing against the virtual machine container-based NFA platform, it is much lighter. All of the network functions are within one process. There will not have context switch. We can easily deploy the network functions of a service chain on a call and do the run to completion. There will not have a cross-call overhead. But everything has two sides. For the function-based platform, all of the network functions are within one process. We cannot leverage hypervisor or operating system CPU scheduler to allocate the resources across network functions. Another big issue for multi-tenant environment, we cannot allow one tenant access another tenant's internal data, like the packets, the flow state information, some statistical counters. Unfortunately, NF or tenant isolation cannot leverage hypervisor or operating system to provide memory protection. In this talk, I will focus on memory isolation. About resource allocation, you can read our paper. Memory isolation is not a new topic. Some work use memory-safe language like Rust Go to provide memory protection. Here, the NetBricks from Berkeley, they use Rust to provide network function memory protection. However, many existing network functions are already implemented by C languages. For example, Brawl or Snot has about 400,000 lines of C code. Rewriting them from scratch will take long development cycle. Softbound and SafeCode use static analysis and runtime instrumentation to provide isolation. This pure software isolation degrades the performance too much, from 2 to 100 times. Can we leverage some new hardware features? Recently, Intel provides a new feature in their Skylake processor. It provides the bound registers and a set of instructions to assist the memory protection. It only has 4 registers, but for application, might be multiple pointers need to be protected. All of us are familiar that because of the limited TLB space, there is a page table and a page directory in operating system for storing the mapping between the virtual address to physical address for an application. Similarly here, there is a bound directory and bound table to store the pointer bounds. When a pointer wants to access memory, it will load the bound from the table to one of the bound registers. Compare whether the accessing memory address is within the lower bound and upper bound. If not, it will release signal and trigger the exception. We use a micro-benchmark HiSet to evaluate MPX performance. Comparing against without MPX protection, the execution time of MPX is about 2.6 times and use about 3 times memory. To narrow down where is the main bottleneck, we test the overhead of each each set instructions. There are only two parts instructions. One part is the load and store. The other is the bound comparison and bound making. What we found is that if we remove the bound load and store instructions, only have bound comparison and bound making, the performance is similar to without MPX protection. If have bound load and the start instructions, the performance will look like same as the full MPX protection. What we learned from the experiment, for the fine-grained memory protection, the lower and upper bound of each pointer is equal to the low memory address and high memory address of the range which it points to. It needs expensive bound load and store for every pointer, which will degrade the performance too much. But what we really care about in a multi-tenant FAPE platform, the providers or tenants care about one tenant cannot access another tenant's internal state and packets. To do so, we propose a coarse-grained memory protection to provide a tenant memory isolation. It divides the memory into large ranges of tenants for all the network function modules, not for every pointer, which can significantly reduce the expensive bound table access. In order to use the coarse-grained protections, we need 3 steps to achieve that. Firstly, we need to classify the pointers and then calculate the bounds and then instrument the code, add the bound checking. A pointer may be from heap, stack, or packet access. We will have the classified component classify the pointers into 3 types. Then let's see how to calculate the bounds for each type. We will provide our own slab memory allocator. Each network function or tenant will allocate space from heap. Here, the colors represent different tenants. The lower and the upper bounds for a heap pointer are obtained from the current memory slab allocator to this tenant. Like here, we have tenant 1, which has 2 network functions. Each network function has some pointers allocated from the heap. The bounds for a pointer will not be exact the low memory address and the high memory address, which the pointer points to. Instead, there are tenants 1's heap bounds, which can significantly reduce the bound access overhead. For tenants packets, we use DPDK, which is fast network I/O library from Intel. It provides its own memory buffer pool. Whatever the real packet size, the buffer size is always 2 kilobytes by default. We use the bound make instructions to dynamically calculate the bounds. For stack, we assume the constant size for each module. Now let's see how we instrument the bound-related code. For heap and stack, at the end of each module execution, we will store the current bounds from the register into the bound table. At the beginning of a module starts to execute, we will load the bounds from the table to a register. For packets, we added bound checking before dereferencing. We evaluated the performance on an Intel Skylake machine with 10 gig NIC port by manually instrument a network function. Here, we measure mark swap without MPX protection as the baseline. The fine-grained full memory protection degrades the performance too much. Our coarse-grained protection has little overhead. If we only protect the right operations, we can further improve the performance. We can achieve comparable performance as the Rust language. Fast aims to provide memory and performance isolation in a multi-tenant function-based data plane. It uses a coarse-grained memory protection to significantly reduce the overhead of accessing the bound tables. It uses a user space scheduler for resource allocation, which consider different metrics like the network function, the batch size, the packet arrival rate, processing cost. Thanks for your attention. I'm happy to take any questions.